NumPy is the workhorse with data analysis. Even if you don't use it directly, it's most probably what you are doing. The libraries that you are using, either pandas or scikit-learn or whatever, they are using NumPy for their work. So you have to be cognizant of NumPy, and you even if you don't use it directly, you have to be careful. And I'm going to change it a little bit. I'm going to the last point here, and imagine that you don't use NumPy directly. You still have to worry about NumPy architecture, because NumPy uses a set of lower-level libraries provided by other systems. These are called BLAS, and I forgot, and Linalg. I forgot the name of the other one, but BLAS and Linalg, I think. It just slipped my mind. But so these libraries are implemented by somebody else. And for instance, the stock library in most Linuxes is not multi-threaded. And but you have many alternatives there. OpenBLAS, for example, or Intel's MQL. And when you have your NumPy implementation, you have to be careful with and check what is the BLAS libraries that are linked, because if they are not multi-threaded, they will not make use of all your cores. And if for some reason you are doing massive matrix processing, you really lose a lot there. So my suggestion, even if you don't program a single line in NumPy, you have to be careful with what are you linking. And if you use, I think many Debian Ubuntu distributions, I think the default linked library, it's actually non-threaded. If you use Conda or Anaconda, they will link OpenBLAS, and that should be enough. You can also link MQL, and there are other alternatives. But I think if you have OpenBLAS and MQL, you should be, even if you don't write a line of NumPy, you should look at this and you should be concerned with that. Furthermore, and there are so NumPy is used by everybody or almost everybody in the data analytics space, and it uses arrays which are n-dimensional arrays, which is essentially an array, right? It's essentially a sequential allocation in memory of data with the same type. In a general term, it can even be a Python object, but there is not a big point in that. Most of the types that we are interested in are booleans or integers or floats, and we want to be careful if they are signed or unsigned. And then we have this blob of memory, this memory view. We have this piece of memory which is mostly managed by NumPy. And which is essentially you have all this data in a CPU native format, let's call it like that, though it's not really, but let's call it like that. And then we have a certain set of metadata, and the metadata is things that you can actually tweak. So for instance, if you have an array of 4 by 5, this is actually a two-dimensional matrix of 4 by 5. You can actually tweak the metadata. You can actually tweak the metadata to be a 1D array of 20 or 5 by or transpose it automatically without doing any costs. And you can invert the direction without inverting the representation in memory. You just tell NumPy interpret this with a different stride. So there are lots of optimizations that can be done there, where you imagine that you have an array and you want to transpose it. You actually don't need to copy the whole array, the whole data in the overall data in the array. You just create a new view and you share the same data. Of course, when you do that, you have to be careful, because you end up with a single array with a single raw data and many views. So you are sparing a lot of memory, but if you change a little bit, if you change one of the views, the data in one of the views, it's reflected in all of the other views. But and I go through that in the book with images, because when you copy an image and you change the original image, you don't see it on the next one. But if you do a view where you invert the image in direction and you change the other view, it will affect both of them. But the concept of views is very important. The concept of views is very important to spare memory and computation with NumPy. Another topic that I go through is universal functions, and this is going to reappear substantially in future chapters, especially the ability to process a single element. Imagine if you have A equals array B, and this is 3. And print A plus B. Okay, where did I do wrong? What did I do wrong? Let me just... Oh, I don't have NumPy here. So I don't have NumPy here. So this would write... something along the lines of 5, 7, 9. Okay, so quite simple. But one could actually do a function that takes an element. This is obviously trivial, right? That does A plus B. Okay. And this function, we could do this in a universal function and apply this function to both the arrays, and this function would be called 3 times, 1 for each element. And there are several interesting things going on here, but one is that this is the way GPUs work, where essentially you have lots and lots of processes doing the same operation. And if this function is implemented in another language other than Python, they can be called in parallel. So this kind of mentality based on universal functions, this kind of mentality can very easily extrapolate to parallel code when using Cython, and can extrapolate to GPU computing. And there will be a chapter at the end about doing GPU computing with Python. And it requires this mentality of, if you have a big array, you don't do a 4 over 4 and do the processing element by element. That's a complete waste, even without a GPU. But you do this element by element processing. There is also another issue with universal functions, which has to do with broadcasting, which I won't go through here because it's not really a processing issue, but I have to discuss it in the book. There is also the issue of broadcasting. But the point here, the most important point here, is that you have a ginormous array. You instead of doing a 4 over 4 of the 2 dimensions or whatever, let's assume it's a matrix, you do a function that processes a single case, and then you ask NumPy, okay, call me this function over the whole array thousands, millions of times, whatever. And again, this is good for GPUs, and it is good for further optimization if you use a lower level programming language.